We're ready to hear Alex Binder's talk on how do we interpret all of these amazing deep learning algorithms.
Hello, I'm Alex Binder, Alexander Binder actually. I am local here from the SUTD Singapore. No, I did not commit any crime in my home country. I really like hot, scorching weather. That's why I enjoy Singapore, and I like to be outside really 2 p.m. on a Sunday actually. Okay, the talk is about explaining decisions of neural networks, and I will also a little bit talk about my own research, layer-wise relevance propagation, but don't worry, I will also show you the disadvantages of my own research. Okay, this is a joint work together with, Grégoire Montavon from the TU Berlin, Klaus-Robert Müller from the TU Berlin, Sebastian Lapuschkin and Wojciech Samek from the Fraunhofer Heinrich Hertz Institute, HHI, Penny Chong from the SUTD, and Yuval Elovich from University of Tel Aviv. Okay, so what we know is deep neural network reach in many fields human or near human performance. One should note here, however, that if you look at some of these fields, like for example, traffic sign recognition or other fields, they are simplified settings, right? This 2011 result on traffic sign recognition, if you look at the data, it's low-res data, right? It's something where a neural network is as good as a human because we simplified the task, right? If you look at ImageNet 1000 classes, right, it's the simplest recognition problem in vision. It's 1000 classes, yes, but it's, how should I say, images with screen-filling objects and only one object class per image. So yes, we reach performance close to that of humans, but it's a simplified setting. If you look at reading comprehension on a squad data set, deep neural networks since 2018 also reach near human performance. But in a certain sense, if you look at this data set, the questions are simplified. It's not general text understanding, okay? Of course, there are fields, right, where deep neural networks reach human performance and they're just unconstrained, right? You lose in Doom against them, right? Don't play poker against deep neural networks, yeah? Put a small camera in your nose when you go to a casino, you know, and then you just look at the cards, you know, and in the background will just tell you what to do in the next step. Yeah? Another thing is it's really hard, lip reading. Their deep neural networks are also better. Okay, so we reach near human performance. Of course, we know it's not the same as human-like reasoning, right? This is Mr. Shout, and I can show you that if I run Mr. Shout through a ResNet 18, this is a modified image of Mr. Shout. He gets classified as a strawberry. Okay? And the problem is here. This is a difference that I used from the original image. It's almost invisible, right? So there are easy attacks adversarial attacks against neural networks that classify totally different from humans. So the good question is here, once we are at this, maybe we need to understand whenever we train a deep neural network, what actually does it learn? Of course, you can do these explanations from mere curiosity. This is Google Translate, right? You can ask yourself, really, does the algorithm understand what it does? But then the question is, of course, what does understanding mean? Does it mean that it gets a high accuracy? Does understanding mean that it knows when it's uncertain about the translation? Does understanding mean that it can explain you why it translated talk into Gespräch, right? I will focus here on a general problem, but on a simplified setting, yeah? Not general understanding. This is a problem to be solved, and I hope we can solve it in the future. The problem is, what made the deep neural network arrive at a decision? Of course, maybe in medical context, sorry, I don't have a brain background. They can be also possibly useful for more than mere curiosity. So what happens here? This is an HE stain of breast cancer with surrounding cells. I did patch-based classification. And what I did, I computed after that a pixel-wise explanation for a patch-based classification. The patch is 100 times 100. This has roughly this size. And on the annotation, which I used for training, the pathologist only said on a patch, cancer is present or not. Okay, it's just a simple classification. Why did I do this? you will never get the pathologist to do segmentation and to, how should I say, draw boundaries against around 500 cells in an image. They will never do that. Yeah. So I did patch-based classification. I did pixel-wise explanation. Here for more, singled out cancer cells, and you see things like lymphocytes or fibroblasts. They get negative evidence. So yes, it can tell you something about what it has learned in some cases. There are many different types of explanations. Two big classes: understanding the model and explaining the single decisions. Yes, I mean, we had already a talk on GANs, right? For example, when it comes to understanding the model, I would like to put your attention also to PPGN, which is more close to GIP sampling and also generates very good pictures. It's a bit sidelined, by the popularity of Ian Goodfellow, but it's worth to check on that. And of course, if you look at activization, maximization, Deep Dream is a famous example, right? This is a famous example for model understanding. The problem is with some of these model understanding approaches, what do they really tell you? Neural networks learn to imitate humans on drugs. Okay. Of course, the things on these types of explanations, this simple taxonomy is too simplified. There are many, many works in between that are worth being considered. For example, mask optimization by Ruth Fong, probabilistic removal is one thing that you can really check on this, a paper by Zincraft, 2016. There are papers on inverting feature representations. So you get a feature map, you want to get out, the input image. So there are many, many things that I won't treat in this talk, but I will focus here not on understanding a model, but on explaining a single decision. Yeah. I will go through a few approaches with their pros and their cons. The first idea what you can have if you want to explain the prediction of a single model, right? You take your predictor, you compute the gradient, and maybe you take the norm of the gradient. Yeah? This has one advantage and one big disadvantage. The gradient explains you which dimensions are most important for changing the prediction. It is not the same as explaining which dimensions contribute to a decision. Whenever you use a gradient, be aware of this difference. This has a very big impact, actually. I give you a simple example, linear mapping, right? There's a linear mapping, f of x, as I should say, weighted sum of the inputs x. Gradients give you just the weights. But for a particular decision, not only the weight matters, but does the input have the same sign as the weight, or does it have the opposite sign? Because if it does have the opposite sign, it gives you evidence against the prediction if you would be in a classification setup, right? So gradients don't always give you what you want if you want to explain the prediction and not only the pure sensitivity, right? Intuitively, you would use instead of this formula maybe if you want to explain what contributed to the prediction. Another thing is if you look at that slide, this is a logistic sigmoid. Here is the decision boundary at 1/2. If you compute here a gradient at this bump, it will in many positions point you anywhere, but not towards the decision boundary. It will give you no information about the decision boundary or how it arrives at the decision, because it's a local sensitivity. Okay, norms of gradients. What is a good thing? They're easy to compute, right? Every toolbox does it. They are easy to understand. The drawback is they can have poor performance in off-the-data manifold examples if you want to explain what contributes to the prediction. Why? This is off-the-data manifold, and in principle, in almost every pixel, you can change the prediction a lot. And gradient tells you, this is a prediction for the motorbike class, gradient tells you, hey, I can add here more motorbikes, I can add there more motorbikes, because it explains you how to change. Okay? Good. Let's go to another method that I find not good before we go to methods that are not by me and which I find good anyway. Approximations by decision trees. I'm very skeptical of this. I tell you why. Again, have same function value does not mean same reasoning, right? You can take a sum of step functions to approximate a linear function. You will get many, many different splitting rules that can approximate the same circle. But in principle, they just approximate the same circle, and they are even wrong about the gradient. Okay? Let's go to something That's, I consider, way more meaningful. Line. Is a paper by, Why Should I Trust You by Marco Ribeiro. What do? They do a local linear approximation around every test sample to explain. So what's the idea? Here's my test sample. I want to explain it. Now I sample many, many points around my test sample that I want to explain. And for every sample point, I compute the function value of my predictor. And then I have pairs, of sample data points and the function value of the predictor, and I can use it to train a sparse linear model. And then I use the weights of the sparse linear model to give me a local explanation around the test point. That is, this is very clear, It's conceptually clear what you are doing. That has one disadvantage. You have to do individual sampling and training for every test sample. Thousands, 100,000s of samples. It's relatively slow. Important is, there are two open parameters in line. The sampling region size and the sample size. The sample size is how many data points do I sample, and the sampling region size is from what region. The region size is important because if I choose it too small, your local linear approximation will converge back to the gradient. And the gradient can be sometimes not a good explanation. Definitely, it's worth to be applied. Of course, you can locally fit more than just linear models. You can fit any other models that you find interpretable. Very nice, clear concept. There are things developed in the neural network community that are not so intuitive. Like, for example, deconvolution guided backprop. I explain you guided backprop because it usually is better than deconvolution. Okay. You backpropagate your gradient. Now, whenever you encounter a ReLU layer, you apply a heuristic rule. You zero out the gradient if either the gradient is negative or the input to the ReLU is negative. Think about that. What does it do? If the input to the ReLU neuron is negative, it means it's an inhibiting input. So I say, I don't want to explain inhibiting inputs. That's the first assumption in guided backprop. The other thing is, I do not want to explain negative gradients, so I don't want to explain gradient contributions that decrease my predictions. I look only for evidence into one direction. And then you just compute this modified backpropagated gradient, and it gives you often interesting visuals that are informative. It doesn't have a theoretical justification, same as Lime, definitely worth to be tried out. Not sure what to do with 10H sigmoid neurons. If you look at the GradCamp package from Selvaraju, they have also an implementation of guided backprop. Okay, I point you here to my competitors for a good reason. Okay, let's go to explanation by decomposition. The idea is the following. Given a prediction over an input sample that contains many, many input dimensions, I want to compute for every dimension a relevance score so that the sum of these relevance scores reconstruct my prediction. Simple idea, histogram kernel SVM over histogram features. This is the SVM output. This is what I want to have. Yeah, okay. In-class question, how do you do this? What should be your relevance? Well, it's clear. I just put the sum inside, and then I have my term. Right? Of course, I showed this already for the linear layer. This works also trivially for the linear layer. Right? Remember the linear layer, you would just take this as relevance decomposition. Okay. What's the problem is, if you just want to have a decomposition, there are many trivial and meaningless rules. Right? For example, I take, how should I say, the function value divided by the number of inputs and just assign every input the average function value. That's meaningless. So we need to have more constraints in order to deal with these non-plausible decompositions. Before I go to additional constraints, I want to tell you one thing. Such a decomposition you can reach by simple math. Right? That's called Taylor decomposition. Yeah? Taylor decomposition is something that gives you precisely this linearization, but you have to choose an anchor point. Right? And the choice of an anchor point will imply an explanation relative to that anchor point. This is your free parameter and Taylor decomposition. Which anchor point do I choose? I give you something specific for classification, an idea. Yeah? The anchor point should be first the root, and secondly, close to the point that you want to explain. Why? For classification problems, right, roots are the points of maximum uncertainty, where your prediction switches a label, right? So if I choose a root for as explanation anchor, I will explain what makes the prediction switch. That makes for classification sense. For regression, other setups, you have to modify this. Of course, you don't need to choose a single root, right? You can take an average of Taylor decomposition against multiple roots to, how should I say, cancel out the noise from a bad choice of a single root. Okay? There is something like Taylor decomposition that does the job. Little disclaimer. Okay. And before I get to very strange formulas, I try to explain why did I do this? Yeah? Why do I just didn't choose Taylor? I started, with high-square SVMs over a bag of words. And the problem is, for the high-square kernel, I can apply Taylor. It's just math. But with the bag of words rank mapping, that was not differentiable. I needed to have something that can deal with non-differentiable cases. This is rank mapping. You don't need to understand it just to know it's non-differentiable because it depends on the rank of your feature to a set of prototypes. Yeah? Okay. So let's start with explaining layer-wise relevance propagation. So we need to derive constraints to arrive at plausible decompositions. The first idea is, same as there can be gradient flow, I can have a relevance flow backwards. I assume each neuron has a certain relevance, and I want to redistribute the relevance from a neuron down to its inputs. And again, from a neuron down to its inputs. And the relevance should be at least approximately conserved up to bias terms when distributed backwards. Why? I want to compare relevances of different inputs, so they should be on the same scale. And if you think of a neuron, inputs can stimulate it to fire. Then intuitively I would give them positive relevance. Or inputs can inhibit it. Here it depends on what axiomatic requirements you want to have. You can have either negative relevance or close to zero relevance. I will discuss this later on. Okay, how to achieve this furthermore in an algorithmic sense? I initialize the relevance of the output to be my function value. Then I decompose every neuron separately into relevances for the input, and I backpropagate the decomposition, so I retain the structure of the chain rule. Okay. Further intuitions. Given such a neuron, a larger input should get a larger share of the relevance. I make an assumption here. Yeah? A zero input does not do anything. This makes sense for these neurons. Yeah? So I want to explain in principle what makes a difference compared to the state where the possible input is zero. And again, it's just an assumption. Technically, your relevance should be in absolute values a non-decreasing function of the weighted input if you do this. Okay, so what do I want to have? Decomposition of prediction that works, with stacks of neurons, that you in principle just do this for every neuron separately. The relevance should be a non-decreasing function of the weighted input. And I want to have, at least in limit cases, a meaningful explanation for linear mappings, because that's what gradient does not do. Good. How do we arrive at this? If you think about this neuron equation, from these things, you can arrive at two basic ideas. If R of y is the relevance that I have already for my output, yeah, I can have the relevance for the dth input is either the output relevance times weighted input, or output relevance times weighted input, where I weight positive and negative contributions separately. Okay? And if I apply this for the first idea, arrive at this complicated rule, I just want to have relevance conservation. This is so-called epsilon rule. epsilon acts as a dampening factor. Yeah? Epsilon, if you have a very large epsilon, your predictions will be smoothed out and very uniform. Yeah? If you take too small values of this, I tell you it can be unstable and noisy. If you take the beta rule, this is more smooth. Again, from this idea you wrote in this rule, looks complicated, never mind. Beta controls the ratio that I want to have of negative to positive evidence in every neuron. So it has a clear interpretation, this parameter. Yeah? And if you have beta equals to 0, I consider only positive evidence, same as in guided backprop. Okay, complicated math. Yeah, sorry, I've studied math. My apologies to that. Let's look how these things look when we apply them to real images. Yeah? This is a Google net. Yeah, something that has millions of parameters. And I tried this out in 2014. I hacked in principle something in a CAFE package. This is the explanation for the Stupa class. This is epsilon rule. This is beta rule. This is an explanation for one of the many cat classes in ImageNet. This is epsilon rule. This is beta rule. Epsilon rule tends to be more noisy, as I promised you. Beta rule tends to be more clean. But when I saw this in 2014, I thought, wow, it's a deep neural network and I can compute explanations. And they make sense. I was surprised by that myself because these things have really millions of parameters. What you also can see here, for example, frogs on green background. Yeah, the motor scooters, you see an explanation which is much cleaner than gradient. Again, see it is a top-down procedure. Gradients don't get high weight. Okay? I'm not doing saliency detection here. I really do a top-down explanation of the predictor. And I can show you in principle that this stuff really works. This is unfortunately my old CAFE package implementation. CAFE is a bit nasty to use. This is a rooster class. I compute, for the best class, which is class 7 ECoG, and you see the flowers get not much weights. Yeah? I have tons of these examples in principle. Whatever, you can take the shark. But this is very simple. It has a very simple background. But Gregoire loves the shark a lot. I personally like the volcano more because it has a bit more background. So I computed, I get the explanation for the class volcano. Okay, back to the talk. So I talked something about, Taylor decomposition. LRP is indeed related to Taylor decomposition. So Gregoire in principle found it out. He's a great theoretician. You can read this pattern recognition paper. If we apply the Taylor decomposition directly to the relevance function as a function of inputs, and you backpropagate, you make a few assumptions, namely a local linear model. Then you find out that if you apply Taylor decomposition layer by layer in a deep neural network, there are certain exotic roots which yield these LRP rules. Yeah? The paper has also better LRP rules than only the ones that we found initially. You can just take a look on that. So yes, it is related to Taylor decomposition rather than gradient. Some notes on that before we go also to some other research from other people. LRP explains the decision relative to the state input equals to 0. That is not always the best choice depending on what you want to do. Yeah? The choice of the root and even of the choice of the state beyond any root is a free parameter. I suggest you really to read the Deep Lift paper by Sri Kumar. They really think this through in all depth, and it's a very nice paper to read from that perspective. Negative evidence. My take on this is it's useful for simpler problem and noise for complicated problem. This is a simple problem, MNIST. Yeah? Here I take a digit of a 3 and a classifier of an 8, and I compute an epsilon rule prediction. And it tells me, look, I think what's wrong with this 8 is something is missing here. Yeah? For a very simple problem, negative evidence gives you something informative. For more complicated problems, rather not. Yes, the Taylor idea works also with deconvolution. This is another thing. I skipped this. Oversparsity. If you look at GradCam, they give you very low resolution heat maps. If you look at LRP, they give you sometimes too fine resolved heat maps. There is a conceptually very simple way to solve this problem. Yeah? You do your LRP, start from the output, backpropagate, 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 backpropagate. You know for every layer, a neural net, some layer, has a certain receptive field, yeah? And you just stop at one layer doing the LRP rules where your receptive field is still large enough. And from that layer, you only, how should I say, backpropagate uniformly to all its inputs and just sum it up. So there is a simple way to be, in principle, being coarser than LRP natively and finer than GradChem does. Okay, disadvantages of my own method. Epsilon rule can be numerically unstable and too noisy. For residual networks, you need to use beta rules. At the point, do you know residual networks, ResNets? State of the art in any image task. Yeah? You have shortcut connections. And where the shortcut connections fuse, you can often have canceling out effects that you have, -3 + 3 equals to 0. Don't use epsilon rule, it will not work. Yeah, because it will just numerically kill you. What in practice works well, epsilon rule for fully connected layers, beta rule for other layers. Yeah. I don't know how good is LRP for sigmoid neurons. Okay. For MNIST, with sigmoid neurons it worked well, but MNIST is very simple. Yeah. Check Gregoire's papers, he has better rules in the meantime. Good. Let's go to a paper that has nothing to do with me, even if it shares a name, but I like this idea very much. The idea is, learn your relevance estimator for the inputs from data rather than some fixed mapping. So you have a one-time pre-training step for pre-training your estimator. Yeah? So in a certain sense, it is not the slowest line and not as fast as LRP, but you learn your relevance from the data. It's neuroscience inspired, actually. If you look at that, the idea that they had is the following. The input X is composed of signal of a noise. And they say, similar to the idea from Stefan Haufe, yeah, a learned filter does not recognize a signal, but it's orthogonal to the noise. That's what it learned. So the weight vector does not follow the signal direction. And the pattern LRP guys then say, okay, how should we learn a signal estimator, yeah, a relevance estimator for a signal? It should capture much information about Y. If it does, and you look at the residue between your input and the relevance estimator, the difference should have low correlation to Y, no matter how much or in what direction I do linearly project it, right? X is a high-dimensional input, it's a vector. S of X is the relevance score for every input, it's a vector of the same dimension, so I can subtract them, right? If you subtract them, I linear project them, the correlation to the output function should be low. So the maximum of this correlation under all directions V should be a low quantity. Okay, that's a coarse idea. Yeah? The residue between the input and their signal estimator should have low correlation to actually your output signal. Okay, then they just in the paper, they just solve it to some equation. And for ReLU activations, you can get explicit formulas how to estimate your signal estimator. You can look up the paper. I just want to give you the coarse idea of that. Yeah, I don't have much time for that. You can generalize this to other activation. So pattern LRP can get you even clearer explanations in LRP. Yeah, you can see this. I'm not involved in this work. That was some Google guys with Klaus. But it's something worth to go if you go for explanations. Okay. 2 last topics. Evaluation. You can compute any explanations. You may want to see if you trust them or not. Yeah? I give you here one proposal how you can evaluate them. The idea is use perturbations on your input data. So, how to do this? I use my relevance scores to order regions. Then I modify the regions in the implied order. And I measure the decrease of your predictor under those modifications. The idea is I have a method that always finds the most relevant regions first and orders them first. Then, in principle, if the most important pixels get the highest score and I start to destroy them, your prediction will decrease very fast. Right? So you can do this, right? I can just order the regions and destroy them in that order, and I can measure the area of my predictor under the graph. The good thing is you can compare this against random orderings of pixels. You have a random baseline. You can use this to compare any kind of methods, and this measure has nothing to do with LRP or any other explanation methods. It's a perturbation-based evaluation, right? Typically, you don't do this with a single pixel, you do this with a region of pixels, namely so that you can allow to capture local correlations in your method. You compute an average decrease over many different modifications of the same region, and you don't need image labels for this evaluation. You only look at your prediction score and at how the area under it decreases. Okay, we did this, we found out, yeah, LRP is better than the convolutional sensitivity, not important, not the most important thing here. Worth reading, deep lift paper. Line, I think Pat and LRP also later RS papers on LRP for text and LSTM. Let's go to applications. What people have done with this, okay? The most natural application that you can have is you find evidence in your data for some predictions. So Sturm et al. Did this for BCI tasks. Yeah, maybe this is something that some of your people can relate. I cannot relate to this really. But people have applied this also to text, for example, to classifiers over text. What I've showed here is nothing image specific. Yeah? You can do this for image-like data. It's not related, but you can also do this with 1D CNNs for text and with SVMs. Yeah? Another application is you can find biases in your training data. This is even more mean. In this paper, we compared the Fisher vector on a deep neural net on Pascal VOC. Is a complicated image data set, more complicated than ImageNet, on many, many classes. And we found, for the horse class, they perform very similar. Then we looked at the heat maps for the explanation. And what we found is the Fisher vector picks up the correlation between the horse class and the copyright tags. We were not aware of this problem before in Pascal VOC data set. After this, we saw why it performs well. Yeah? So it can help you to find your biases in your data. And these copyright tasks, they are something, if you would look carefully, you would find them. But Pascal VOC is 10,000 images. Yeah? It's very hard to browse this through. You just get crazy when you do this. I show you another setup. Fluorescent imaging of breast cancer. I got this from my medical contact. I run a classifier, I computed the predictions. It should in principle find breast cancer cell nuclei, so these bright things. And if you look at the heat maps, there is lots of positive evidence on, how should I say, stroma. Yeah? Why did it happen? Okay, it was a data set with a few hundred images, not very much. I looked into the data. Then I saw it, The data always had large amounts of cancer cell nuclei. They were never patches with only background. I got this data from Frederick, and of course you just look at them, but you don't see this bias actively. So what did I do? I took the training images. Yeah, this is a test image. It was not used in training. I took the training images, extracted manually background patches, inserted them into the training, retrained. After that, my explanation becomes much more meaningful. I don't get hallucination on stroma anymore. Yeah? So finding biases in your training data is something that also can help, and in particular neurosciences can be useful for you people. Here are some papers. One closing remark. If you want to do deep neural network training, because I see it's more tutorial style, do not make the MNIST mistake. Do not train your neural network from scratch. Do transfer learning whenever you can, even if you initialize something on MRI from ImageNet. I give you a very quick, spontaneous example. There was some small, I don't have internet, never mind. There was, how should I say, in ImageClef, a competition on tuberculosis CT scans, black and white. My PhD students had 2 weeks to train a model. They used transfer learning on 2D images. There were many groups that did training from scratch with 3D models that are much more meaningful as a model. But in the end, our model was best because we did transfer learning. So whenever you have the chance, initializes from weights from an existing halfway similar task. This is very important to get things right. Here are some links. If you want to do a tutorial on how to use LRP in Python, I don't have time, my time is up. you can go for this website. The general website, heatmapping.org, sorry for the title, I didn't choose a name. And it has also an implementation of LRP for LSTM, recurrent neural networks, if you're interested in that. That works surprisingly well. There is an LRP toolbox with MATLAB examples. I think many of you are still in MATLAB. Yeah, that's very okay if you do. There is also TensorFlow wrapper. There is an experimental and mixed-net integration, and you can also just try out the demos. That's all for the talk. Sorry for going, 5 minutes over. That's it.
So we have time for a few questions, if anybody has any questions. I'm actually kind of curious if you could comment on the perturbation method, which is, I think, kind of similar to sensitivity in a way, but for some reason it makes me think of AdaBoost, because it makes me think of how one layer might change the outcome by fixing that which is misclassified by a previous layer, and how things are all connected. And I ask you about this because I know that in Klaus Robert Mueller's early work, he pointed out some of the problems with AdaBoost. So I thought maybe you would have some comments on that.
Yeah, here actually the idea was a little bit different. The idea was originally that I wanted to have a generative process that, how should I say, can mask regions. In the end, we did go without a generative process. The idea was here really more, not so much inspired by AdaBoost, but really what happens with the result if I take away the most important regions, and how do all the methods report me as what do they think is most important regions. Of course, the problem is optimally. You don't do this with these very simple patches. You do this rather with a generative process, to, like a gun, for example, to replace the patch by something hallucinated. What is here important? How is it different from sensitivity is? You do the perturbation on a larger region, whereas the gradient is per pixel. So by doing the perturbation on a larger region, you, how should I say, can remove a region including a relevant context. Because I think usually it's not a single pixel. You need to be at the right scale of context to have, how should I say, a meaningful decrease. And that's something that gradient does not account, because it just looks, at every pixel separately.
I have kind of a follow-up question. The perturbation, it sounds like a combinatorial problem to solve. But is that correct?
Like what?
Is it a combinatorial problem to solve? Like finding perturbations so that your predictions change or they do not change?
No, I have my explanation methods sorts me the regions, okay? I choose a region size. Then the explanation method sorts me the regions from what it thinks are the most important to what it thinks are least important. And then you have to apply over the region a perturbation, how should I say, that masks it. And yes, there is a problem, of course, what perturbation to choose. In the paper, what I did when I did the evaluation, in principle, I took many different perturbations of the same region and I averaged over that. This was the way to deal with that. Of course, really, in this point, you can use generative processes like GANs and others to mask a region by some other content, yes.
Are there any other questions? If not, let's give Professor Binder another round of applause.